In this assessment, we're asked to synthesize the molecule on the right from the molecule on the left. And it's recommended that we would probably do this in 4 steps. Maybe you have a way that'll do it faster. We're going to do a 4-step synthesis. Now, anytime we do synthesis, we want to work backwards. This problem gives us an advantage, though, in that we know exactly what we're working backwards to. And so we can kind of start by identifying what part of this carbon framework in the molecule on the right is already present in the molecule on the left. We get a big clue because of this tert-butyl group. And so let's number our carbons that way. If we do 1, 2, 3, 4, 5, and 6, we know that 3, 4, 5, and 6 are part of the tert-butyl group, so that's probably this. The next 2 carbons attached, probably carbon 2 and carbon 1. What we're adding then are these 2 ethyl groups. Now let's think about, as a way of starting our synthesis, working in the backwards direction, what reagent, what reactant, what functional group can we react with to add to make 2 new carbon-carbon bonds while at the same time generating a tertiary alcohol. The way we're going to do this is going to be to add to an ester. If we want to do it in 1 step, we can add to an ester. What can we add to the ester? We could add a Grignard reagent or an organolithium. Let's use organolithiums just for fun. So we'll use 2 equivalents of the organolithium. If you used a Grignard reagent, you would be correct also. Now notice that this oxygen is protonated. That's going to require step 2, an acid quench. But essentially, we're going to add our nucleophile 2 times. We're not going to show a mechanism, but we can think about it. The negative charge, the lone pair, adds to the carbon of the carbonyl, pushes the electrons up. They collapse down, kick out the good leaving group, and then the ethyl adds a second time. Now, at any point, we should look at this molecule, still with our carbons numbered, and ask ourselves, is there a way to go directly from this alkene at carbon 1 to make it an ester? And the answer is no, there's not. But what can we do? What can we do at carbon 1? And so we're going to do this combination of working forward and backwards. We know we need to get an oxygen at carbon 1, and we'd like to get it to the oxidation state of an ester. Well, let's go ahead and put that oxygen at carbon 1. For that, we can use hydroboration. So step 1 is to add BH3. Step 2 is to react the resulting compound with sodium hydroxide and hydrogen peroxide. This will give us a hydroxyl group at carbon 1. Now, synthesis can be challenging, but hopefully you start to see where this is going, and over time you develop the intuition to be able to do this on your own. But we have a hydroxyl group at carbon 1, and we need to get it to an ester. We don't have a way to do that directly. But what can we convert into an ester that we can convert a hydroxyl group into? A carboxylic acid. So we can convert the primary alcohol into a carboxylic acid. So we'll squeeze that in here. And then we can convert the carboxylic acid into an ester. Now, I don't have a ton of room. I didn't leave myself a ton of room for the reagents. The reagents that we would use here are chromic acid and water. That's going to give us the carboxylic acid. The reagents that we'll use here to go from a carboxylic acid to an ester, that is the Fischer esterification. We would use ethanol and sulfuric acid. So hydroboration to make the primary alcohol to the carboxylic acid to the ester, 2 equivalents of the organolithium, and we make the tertiary alcohol on the screen.